All right, functions class. We're back for video 2. Okay, we're going to go over the homework. Let's do it. I think I'm just going to do them all, but I'll try to go as fast as I can. So, number 1 from page 188. Yeah. Note that in these problems, you were not actually expected to come up with a function. You're just supposed to understand the patterns of the data. So okay, let's do it. Number 1, f is a linear function, and f of 2 equals 1, and f of 5 equals 7. So find f of 8 and f of 11. So the idea is here's x. Here's y. This is 2, 1, 5, 7. And then there's just like 8, 11. So what we do is we exploit what we know about linear functions, which is if they go up 3, and this goes up 6, then when it goes up 3 again, it also has to go up 6, and it also has to go up 6. So this is pretty boring. This is therefore 13, and then this is like 19. Okay, more. Number 4. F is a direct cube variation function with f of 3 being 0.7. So 0.7, f of 3 is 0.7. So what is f of 6 and what is f of 9? Well, now I use what I know about direct cube variation functions, which is that, make sure I get this right, yeah. If you increase the input by a certain factor, like times 2, then the output will increase by times 8. And if you increase the input by times 3, then the output will increase by times 3 cubed, or times 27. So that's it. This is just like 5.6, and this is like 140, 1.18.9. I have no idea if these are the right numbers. It's really helpful when you guys are sitting here in the room, so I can just be like, is that right? And then you all just say yes. Anyway, I think that's right. 140 and 49, 189, yeah. Cool. More. 5 says, yo, this is an inverse square variation function. An inverse square variation function means that y varies inversely with x squared. In other words, like it's like that kind of thing. Or you could write it as y equals k x to the negative 2. All right. So f of 5 is 1296. Oops. F of 5 is 1296. And the question is, figure out what f of 10, 15, and 20, what those y values are. Well, if this goes up by a factor of 2, then according to this must go up by a factor of 2 to the negative 2. So this is going to go up by a fourth. And if we increase by a factor of 3, then this is going to go up by a factor of 1/9. And if this goes up by a factor of 4, then this is going to change by a factor of 1/16. Pretty sure I'm doing this right. So 1296 divided by 4, that's probably like something 324. Yeah. And if it goes up by a factor of 3, then this is going to go by 1/9. Is that even going evenly? Oh, it does. What is that? So it's going to go in 100 and 40. What the hell am I doing? 140 360. Oh man, I wish I was smarter. 900, and then that's going to leave 396. So that's like 360 and another 36, so 144, I guess. And then 16. These like basic things I should know. So divide by 4 again. So that's something 675 and 681. Is that right? 320. Yeah, I think that's right. All right, I'm 30% confident in that answer. This is taking way too long. I'm sorry if you're bored. Oh, 13 we kind of and 15 we did end the video, so I'm not gonna assign those for homework. Let's move on to the next page, which was a little bit slightly more exciting. So then they gave you some data, and you had to figure out what the function was. You had to figure out first what kind of function it was, and then like what the function was. So let's do this. 2, 4, 6, 8, 10, and 2700, 2400, 2100, 1800, 1500. Yeah, let's do it. Let me do a couple of these at once. What am I doing? 1 through 9 odd, so that's 3. This is 2, 4, 6, 8, 10. And this is 12, 48, 108. This is riveting video. 192, 300. All right. Check the frame. Yeah. Looking good. Okay, so we do it. What? I have to search around for the various possible patterns. Oh, this one is like so boring, man. What's happening? We go up by 2. We go down 300. We go up 2. We go down 300. Up 2. Down 300, up 2, down 300. Oh baby, I have seen you before. You must be linear. And now it is just a matter of figuring out what the linear is. It looks like we're going down 150, so I guess the slope is negative 150. So this is probably like y equals negative 150x plus something, I don't know, 3,000? Is that right? I think that's right, because then you plug in 2. Yeah, looking good. Hopefully this is the right answer. All right, number 3. Let's see what the pattern is here. Okay. Here, I'm going up by 2. And this is increasing by a factor of 4. Here, I go up to more, no wait, what am I doing? This is times 3, so not up to, that was the wrong pattern. Times 2, and here times 3, and my output increases by a factor of 9. And then we increase by a factor of 4, and the output increases by a factor of, that's like some number. I hopefully guessed that that is 16. Is that right? Times 16, 160, and 32. Yeah. And finally, if we go up by a factor of 5, the output is going up by a factor of 125. No, what? Times 25. Yeah, times 25. Okay, so what is the pattern when I increase the input by a certain factor? The output increases by that factor squared. And that is the telltale sign of a direct square variation function. So y has to be of the form kx squared. And now you have to figure out what k is. Well, if you plug in 2, it's supposed to be 12, so k must be 3. So I claim that this is y equals 3x squared. Let's just quickly check that. Looking very good. Yep. Okay, good. 2 down, 3 to go. Let's do 5 and 7 and 9, and then we're going to learn something new. Let's move this guy to over here. Yeah. So, I'm sorry this is so slow. I know I could go a lot faster. Maybe you can figure out some YouTube way of watching this video at like double speed. So this is 2, 4, 6, 8, 10, or maybe you can just multitask while you do this. Yeah, man, these numbers don't look nice. And then this is 2, 4, 6, 8, 10, 1800, 450, 200, 112.5, and 72. While we're at it, I'll put up number 9. That's 2, 4, 6, 8, 10, and like these gross numbers. That's 900, that's 100, 11.1 repeating. That's probably like 11 tenths or something, right? Then just some other gross numbers. I don't know. I'm too bored with that. Okay, let's do it. What is going on here? Oh, this might just be like linear or something. Because, no, it's happening. This goes up by 26, this goes up by 26. Yeah, this is totally boring. This goes up by 26. 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 This is just linear. Plus 2, plus 2, plus 2, plus 2. This is linear. I'm so bored. Maybe it's even a direct power variation. Is this just like y equals 13x? Is that true? I'm pretty sure that's true. Okay, done, bored. Here, what is going on? Well, now we go up by 2, and the output changes by 4. So I just multiply by 1/4. But now I go up by 2 again, and now the output has changed by 1/9. And now I go up 2 again, and the output has changed by, presumably that's 1/16. Is that true? Probably is. 900 over 8, yeah, it looks about right. And here I go up, what am I doing? Kind of messed up this left side over here, let's try this again. Well anyway, this is going up by 1, what is that? 200 over 8, 25th. So, oh yeah, so I had this kind of wrong over here. What I should really be saying is, this is going up by a factor of 2, this is going up by a factor of 3, this is going up by a factor of 4, and this is going up by a factor of 5. And so it is fitting the pattern, again, of a direct nth power variation. In particular, the power appears to be to the -2. So this is going to be y equals k over x squared, I'm pretty sure, because that's what direct nth power variation functions do. Yeah, so what is it? When I plug in 2 4s, there's just like y equals 7200 over x squared, is that right? I think it is. I think that's right. Okay, 9. What's going on now? Well, this is, here we're going down by 9. So that's times 1/9. And then I think those numbers are just, do I just keep dividing by a 9th? I think I do. I gotta get 100/9. Never mind what I wrote before. That is the right answer. That is what 11.111 repeating is, and then I think I just keep dividing by 9. So this is like 100 over 81, which looks like about that number, yeah. And then this is like 100 over times another 9. Oh my god, blanking, 243. Yeah. So, is that right? Yeah, that's right. Because that's like about 1. No, something is wrong. Oh, because not 9. 1 over 729. Yeah. So that is what's happening from each step to the next. And then what's happening here? Well, we're going up by 2, up by 2, up by 2, and up by 2. There's a lot of different ways to think about these, by the way. This is not the only way. But so, all right, what kind of function has the habit that when you go up by a constant, the output increases by some fixed factor? This must be exponential. And as I said before, exponential in the sense of it must be of the form a b to the x. So this is of the form a b to the x. And you can probably even just look at it for a second and figure out what the x is. It looks like, or what the b is, it looks like b has to be like a third, right? Yeah. So this is y equals a 1/3 to the x. Don't ask how I did that, I just kind of did. I think most of you can, okay, I'll show you the lame way in a second, but you can kind of just see, because it's kind of just like jump, jump, and then that went like jump, jump, so it has to be a third. But there's also another way to calculate it exactly if it's not so obvious. Okay, by the way, what's a? If I plug in 2 1/9, does a have to be something huge, like 8100? Is that right? Oh yeah, I guess I could put a 0 here, and then I would just multiply, yeah, so it's 8100. So y equals 8100 times 1/3 to the x. See what I was talking about here? If you put a 0, then, why did I draw these so stupid? Sorry, plus 2, plus 2, plus 2, plus 2. So if you kind of extend the chart with a 0 here, and that's also plus 2, so the pattern has to be, again, to multiply by 1/9, so it has to be 9 more. Yeah. Okay, what's the lame way to do this? The lame way to do this is to know that it's of the form y equals ab to the x, and just plug in and say, well, that means that 900 must equal a b squared. And then use the next data point, which says that 100 must be a b to the 4th. And then you have two equations, you can upside down divide them. If you upside down divide them, you get b squared equals 1/9 and b equals 1/3. Here you can kind of just do it in your head and feel it, but this is the way if the numbers are ugly to figure that out. And then once you know b is 1/3, you use a point and you figure it out. Okay, good. That was this homework. I feel like this homework is really easy. I'm really sorry. I feel like in class we could have gone over this in 5 minutes, so I just wasted some extra 5 minutes of your short lives. But now we will learn something new. So we understand how to recognize linear, direct nth power variation, and exponential functions based on patterns in data. And now what I want to do is I want to recognize quadratic functions. Okay. move this camera around. Yes, I'm just sitting in a room by myself. All right, let's do this. So, where's the book? So, suppose I give you a quadratic. We might have already talked about this before. Anyway, suppose I give you a quadratic. They just come up with a quadratic. Yeah, let's just use what the book does. Why not? So, we take a function. The function is 5x squared minus 37x plus 132. Disgusting function. And now let's look at some data. Here's the data. Okay, and this is kind of artificial because the data is coming at these discrete intervals. And so this thing that we're discovering only works in this case. So let's suppose you're measuring some quantity and this goes, what happened is we just went up by 3, then we went up by 3, then we went up by 3 again. Okay, let's see what happens to the outputs. Let's see what happens to the outputs. Well, if you plug in 1, you get, I don't feel like doing this, the numbers are in the book, you get 100. Yeah. If you plug in 4, you get 64. If you plug in 7, you get 118. And if you plug in 10, you get 262. Okay, this is very strange data. Personally, I would not be able to look at these y values and to notice any particular pattern. The numbers do go down and then back up again, so it's probably not, well, it's definitely not linear or exponential, because exponential functions increase everywhere. It's definitely not direct nth power variation either, because those are also all increasing or all decreasing. So what is going on here? Well, actually I know the answer, it's quadratic. So this is kind of a stupid example, but what is happening, what can we say about this quadratic data? Well, let's look at the differences from one number to the next. So from 100 to 64, this went down by 36. And from 64 to 118, this went up by 54. And from 118 to 162, we went up by 144. If I did that right, I think I did. Okay, so I don't know what to say about that. But perhaps now you notice something. You can now look, oh, and these have a name. These are called so-called first finite differences. Finite differences. In other words, we're looking at the difference in the y values between successive, or the difference between successive y values, as long as the input is increased by some constant amount. Well, now you can look at this and you can see, aha, this went up by 90, and this also went up by 90. And these are the so-called second finite differences. And we did this already back when we talked about exponential functions. We kind of made all these pictures on the board, I hope you remember, and we learned certain things about like linear functions. Linear functions increase at a constant rate. Quadratic functions increase at a linear rate. And so you can sort of think of these numbers as being the rate at which the quadratic function is increasing. And the rate at which the quadratic function is increasing is linear. And so there's a theorem that says that given a function, if the second finite differences are constant, then it is a quadratic. Or rather, quadratics have constant finite second differences. And this is basically like some baby calculus going on here. So if you know some of that, then that's interesting. Okay, let's just prove it. We do the proof in general, it's not that hard. So let's take any quadratic function. So ax squared plus bx plus c, just a generic quadratic. And now what I'm going to do is make the chart x comma y, and now let's take some arbitrary input x, and let's track what happens if I increase the function by d, increase the function by d, increase the function by d again. All right. You can take a minute and like maybe do this right now. I'll just do it. Okay, so if I plug in x, I get ax squared plus bx plus c. If I plug in x plus d, I get x plus d squared plus b x plus d plus c. And here I get a plus 2d plus b x plus 2d plus c. And ax plus 3d squared plus b plus 3d plus c. Okay, now we do some math. Could I write this out a little bit better? Yes, I could. This is going to be ax squared plus 2a dx, right? Yeah. Plus a d squared plus bx plus bd plus c. Is this in the frame? Just barely. Right. And then here, what do we get? We get ax squared plus, that would be 4, so that's going to be a 4a dx plus 4a d squared. And, plus more. Plus bx plus 2bd plus c. And this will be ax squared plus 6a dx plus 9a d squared plus bx plus 3bd plus c. And then maybe I'll write the original back over here. It's ax squared plus bx plus c. Okay, so now that that's written out like that, let's look at the second finite differences. Or no, let's look at the first finite differences. So what's the difference between the first one and the second one? Well, same. So it went up by 2a dx plus a d squared plus bd, I think. Yep. And now from here to here, it went up by, well, I got another 2a dx, so it went up by 2a dx, and then it went up by 3ad squared, and then it went up by bd. And then from here to here, it went up by 2a dx. Now it went up by 5ad squared, and now it also went up by a bd. So that is the gap between the y values. That's by how much the function increased when I increased the input by d. Now let's look at the gaps in the gaps. This went up by 2ad squared, and this went up by 2ad squared. Yeah. And a is a constant for the particular quadratic, and d is also a constant. And so what we have just proved is that for any quadratic whatsoever, the second finite differences are constant. And not only that they're constant, but what that constant is. That constant is 2ad squared. And again, this is basically saying that for any quadratic, if you jump by d, or if you take any quadratic function, this is what this is, you take any quadratic functions, add d to the input. I don't know what this says. I don't know how to say this without using calculus. But it says that the rate of change of the function depends on twice the leading coefficient and the square of the gap. Okay, good enough. All right, let's do one quick example. Is this thing still taping? Da 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 da. It is still taping. Okay, so here's the one quick example. Oh, that was just seagull. That was just like birds in the background. All right, let's do one quick example. I don't know what homework I was going to assign on this topic, but man, 191. Yeah. Oh, I was going to assign 3, 6, 7, and 0. Okay, so let's do number 4, and let's hope that number 4 is actually quadratic. Hope it is. Good. Let's do number 4. So here's number 4. Number 4 just gives you some numbers, and it says, yo, what is this function? So 2, 3, 4, 5, 6. This is so incredibly artificial, by the way, but we are building, once we understand deeply certain functions, we are building towards applying this to real data, or at least fake real data. Okay, so the directions are find second finite differences and tell whether it's a quadratic, and then figure out what the quadratic is. Okay, so you just jump in. What happened? This went up by 34. Yep. This went up by 44. This went up by 54. And this went up by 64. And then, if you look at the differences, they are 10, 10, 10. Ding, ding, ding! This must, in fact, be a quadratic. And not only do I know it's a quadratic, but I know that 2ad squared is 10. And d in this case is 1, because I was just going up by 1, which means that a is 5. And so once you know that a is 5, I don't actually have a system of 3 equations and 3 variables anymore. I have just a system of 2 equations and 2 variables. This tells me that this must be in the form 5x squared plus bx plus c. Now it's just a matter of doing it. I get 109 equals plug in a 2, and I get 20 plus 2b.